continue today with our discussion on the environmental factors that affect soil fertility. And we left off with pH last session. And we learned that nutrient availability is to a large extent determined by pH. And here's another twist to that, and that is that also the formation of and stability of secondary minerals and primary minerals are affected by the pH, as well as the level of oxidation. And you can see here when you look at the Nernst equation and the equilibrium concentrations, for instance, for a manganese oxide, you see that not only the protons play a role here, but also the electrons that influence the stability to manganese 2+. And here's these stability diagrams, and they're go a bit beyond of what I want to discuss with you here, and you will be bothered with them much more in a soil chemistry class. But it's really, you should at least once have a look at that. Down here we have the pH from 2 to 12. Out here we have the oxidation state, so negative redox potential. Positive redox potential means there is air. Negative redox potential means reduced conditions. And here for the iron complexes, you see that if you decrease the pH, you can move from an iron oxide, here hematites or goethite type of oxides, to iron 2+. So it seems that the pH influences the stability, but also the redox potential here. And the same over here with the manganese oxide complex and dissolved manganese. And you'll get this information in much greater detail in a soil chemistry class. This is really one of the charts that you have to know by heart. So you can just try that out if you can paint this blindly, so to speak. This is just a sketch how the pH affects nutrient availability. And the larger green bar means that there's more availability at this pH range, and the smaller or narrower means lower availability. Just off the bat, which elements are missing from this here? What important elements can you see that are not in this chart? Nitrogen. And? Phosphorus is there. Sulfur, yeah. So nitrogen and sulfur are not there. And why would you think they're not there? What's the reason that they're not there? That's a good... so does not really, I mean the not really is important also, but it's because it's not only not. We have seen before that nitrogen mineralization, for instance, is can be affected by pH and nitrification. But you're right, it's not really affected. And why is that? Think about what forms these two elements are in the soil. Nitrogen and sulfur are predominantly in organic form. 95% or more is in organic form. Whereas all the others, P can be 80% in inorganic form, maybe sometimes only 30 or 40. But all the others are basically in inorganic form. So the pH and the change in electrostatic adsorption over the range of pH doesn't really affect nitrogen all that much. Yes, nitrate will be absorbed more vigorously at low pH in soils if you have a lot of variable charge. But 95% is in organic form. So the release from organic matter is really what drives nitrogen availability, not really the adsorption. Yes, Helen?
I'm sorry. What is it showing along the pH range? Is that availability? Is it changing redox states? I just didn't understand.
No, I have not at all talked about this. I've been still with why nitrogen is not at all on here. Why does pH not affect nitrogen availability all that much. Now let's look at that. Yes, Helen. So this means, for instance, for phosphorus, if we look at phosphorus, it means that at very low pH, 3 to 4, phosphorus is not very well available. It means that between 5, 5.5, 6, 6.5, phosphorus is very well available. That's why I picture this large bar. And then to higher pH, again, the phosphorus is not very well available. Why is it not very well available at low pH, phosphorus? What happens at low pH with phosphate? What happens?
They stick some protons in the phosphate, like HPO4 and H2.
Yeah, and what reactions does phosphate engage in at low pH? What's the big thing with phosphate? Fixation. It fixes to aluminum and iron oxides at low pH and forms covalent bondages. So it's just not available for plants anymore. At high pH, what happens at high pH? At high pH, there is no free aluminum and there is no free iron. What is happening at high pH, at pH of 7, 8?
Precipitation.
Yes, with precipitation, with? Well, what's prevalent in lime soils? Calcium. Yes, calcium phosphates at high pH, iron and aluminum phosphates at low pH. And there's a window in between at 5 to 6.5 where neither there are too many calcium ions around nor are there too many aluminum and iron ions around. So there's a window of opportunity, and that's where we want to be with our soils, between 5.5 and 6.5. If we go too high, we're getting calcium phosphate formation and reduced availability of phosphorus. If we go too low, we get iron and aluminum phosphates. Potassium and magnesium should be that in neutral pH and higher pH we have good availability. At low pH we have reduced availability. Why reduced availability? Also for calcium, by the way, at low pH. Why that? Low CEC. So low cation exchange capacity, exactly. That means the calcium and magnesium cannot be retained on the exchange complex, and so it's leached out. It simply can't cling onto the soil. Why for potassium and magnesium at high pH? Why it's a little bit reduced? That's a more difficult question, and we haven't really gotten there yet. But anybody an idea? That's competition between calcium and potassium, for instance. At very high pH, we have lime soils, we have a lot of calcium, and the plants just have no possibility to grab out the potassium. So it's just competition between calcium and potassium on the exchange complex as well as plant uptake. But that is something we will still be discussing, these interactions. But calcium, really, the higher the pH, the more calcium availability. Just lime soils, they have a lot of calcium. There's no problem. So the base cations, high tendency, higher pH, better availability. The micronutrients, tendency, lower pH, better availability. So exactly opposite. Micronutrients, lower pH, better availability. Macronutrients, calcium base cations, higher pH, better availability. And you see here, and why is zinc, copper, manganese, and iron at high pH low availability? Those of you who have discussed with group 8 in the lab definitely have heard that. What happens at high pH with these micronutrients, copper, zinc, iron? What's group 8 all about in the lab? Joseph?
Sequential extraction of these micronutrients.
Yeah, and what was the agroecological background of that? Why were we interested? What soils were these orchard soils that that, that were to be investigated. Were these low pH soils or high pH soils?
High pH.
High pH. But what is high pH soils? What kind of soils are these? What needs to be there? We just discussed it with phosphate.
Calcium, magnesium.
Yeah, so there's lime soils, carbonates, calcium carbonates, magnesium carbonates. So what would these form? I think we had it also earlier.
The complex with
Yeah, or precipitate. Complex we talk about more if we talk about organic complexes. But these are more precipitates, zinc carbonates, copper carbonates. So all these micronutrients, copper, iron, manganese, zinc, the availability in lime soils is, or calcareous soils is very, very low. They're just precipitated. The plant doesn't see it. Only molybdenum and boron are a little bit different. And the reason is, I already put that here for boron, they are actually not present in the soil as ions, just as a metal ion, but they are present as molybdate, MoO4, and borate. And for boron, it's a little bit more difficult even. So they're not present as a cation like these. These are all present as cations. Copper plus, zinc plus, iron plus, manganese plus. Whereas these, molybdene is not as molybdene plus present in the soil, but as molybdate minus. So it's a molybdate, like a sulfate and a phosphate is a minus, a nitrate. These are all anions. Also the molybdate, and you see here the borate, is also present as a anion. That's why they look different than the other micronutrients. And actually, molybdate has a lower availability at low pH and a higher availability at high pH. And borate has a very a more complex behavior because it's actually only charged somewhere around here, and down here at the lower pH it's not charged at all, so it can be leached out fairly easily. But boron actually we have very often in sodic soils and in arid soils we have lots of boron to the extent very often that it can be toxic. So this is really very, very important, and I encourage you to have a very good look at that. This is one of the central pieces. We have been talking especially with group 1 and 2 in the lab about the effect of plants on nutrient availability, and we have this experiment in the lab that we look at the availability of nutrients in the soil versus what that does for plant availability and the uptake and growth of maize. And we already recognized, and we discussed that in lab, that actually it could be that when we measure plant available nitrogen or calcium and magnesium in the pots without the plants, we probably don't capture what the influence is of the plants on nutrient availability. And this is exactly what I want to show here. So in this study, they looked at the bulk soil pH at first, and moving then closer to the root surface, what they call a rhizosphere, so probably the first 1 centimeter around the root or half a centimeter, and the rhizoplane, so very close to the root surface. They measured the pH here, and you can see these are different planting dates and different stations that they measured that. But in all, you can see there's always an increase, and it seems in most cases there's a significant increase from the bulk soil pH to the rhizoplane pH. So there is a significant impact of the rhizosphere, the roots, on the pH environment. And we've seen earlier that, for instance, that one of the techniques that roots or plants develop to take up micronutrients is, for instance, to exude low molecular acids like oxalic acid or citric acid to complex copper, for instance, and take it in. So there are strategies of plants that can solubilize nutrients in the rhizosphere. And here you see an example for a pH increase. And that actually has an effect on nutrient availability. Here you see that actually it's exactly, unfortunately, it's the same study, but they did it the other way around. So the low pH, the high pH is closer to the rhizosphere, to the root surface, and you see that the aluminum concentration decreases with proximity to the root surface because the pH increased. That's of course very nice for the root because aluminum is toxic for the roots, and a low or almost zero aluminum concentration in the soil is very conducive for root growth. And it seems magnesium concentration increased, ammonium, nitrogen concentration increased, phosphorus in water and phosphorus in the Bray solution increased, nitrate increased, calcium increased, potassium increased vaguely. So it seems that there was a good case here to be made that actually nutrient availability increases the closer you go to the root surface. And also in this study where they looked at nitrogen immobilization and mobilization, they found in pots that had no plants versus pots that had plants at 2 days after planting, always a significantly higher available nitrogen concentration in the pots that had plants. So also here you can see that nutrient availability increased with the presence of plants. And that's of course a bit difficult with our tests that we now develop, that we said, yeah, we want to look at nitrogen availability in the soil and we use mineralization as the parameter, for instance. We do that in pots that are not cropped to any plant, that we have probably some challenges here with coming up with real numbers. But we also discussed that in these bioassays, we were not actually simulating real conditions because it's in the lab here at artificial temperature and moisture. So we are more interested in the comparison between treatments rather than an absolute number. So that wraps up our part on the environmental factors, on their influences on nutrient availability. And we already, with our little discussion now, we moved further into soil fertility evaluation. And I want to discuss today with you different possibilities for soil testing, for plant analysis, using fertilizer trial, and then move into traditional soil evaluation for assessing soil fertility. And this will sort of give you also the framework for all the different labs that we have in our laboratory session. And most of you have had one of those assays done already throughout the last weeks. So here, total soil nutrient contents. When are we interested in that? When we really are interested in total stocks, what is the total amount in this ecosystem that is below ground? That can be an important number. Also, we have learned that despite the fact that probably in many soils there is a pool in soil that is not available immediately to plants, it corresponds in some way to the available content. We had this concept of quantity and intensity with these two different buckets that are connected with each other. So we might be interested in this relationship between non-available but total nutrients and the available portion of it. But as we discussed in the lab with group 1 especially, it seems that in our assay total nitrogen in the soil would not be a good proxy for nutrient availability probably. So it might not be per se a good assay for a good analysis for determining nutrient availability. And there are a few procedures, for instance, for nitrogen with Kjeldahl or dry combustion. We will use dry combustion in the lab. Phosphorus, you need to digest the organic matter and destroy the clay minerals. Sulfur can be by dry combustion or wet digestion. And the other micronutrients and base cations, also you have to digest the entire soil. And I don't want to go in great detail into those, but that is then available to you in your script. Soil nutrient extractions, very often they target then plant available, the bioavailable portion of the total nutrients in the soil. But sometimes also we are interested to make an extraction to make an assay of mobile nutrients, or maybe those nutrients who can be leached. I think Helen, for instance, that is what you are interested in your lab, that you want to compare highly contaminated soils with manure, in our context contaminated soils, whether what portion of that phosphorus in soil is mobile and can present a hazard for surface pollution of waterways. And types of extracts, there are a slew of extracts: water, resin, salt, and we'll look at these right now. Just making a water extraction, or looking at the soil solution, is very often interesting to get at the immediately available portion of nutrients. Those nutrients, everything that's in the soil solution, plants can take up. There's just by mass flow, the root sucks in the soil water, and with it flow the nutrients. So that is definitely plant available. Then there are some water extractions that with hot water for boron it might be useful. And here are some contraptions that show you how that could work with soil solution extraction. And here you see a soil pit where we instrumented with different water measurement devices, tensiometers, TDR, automated tensiometers, and also these so-called suction cups where you go from the side then in and suck out the water. And this works as depicted here. You have a pump somewhere, and you have a guiding tube with a small capillary inside that ends in a porous cup, in a suction cup, or lysimeter also called, very often a suction lysimeter. These are ceramic cups that have very, very fine pores, and if you apply a suction, it will suck the soil solution in without sucking any of the soil in, and then you can sample that into a bottle and periodic take your sample. And you can mount that from the side or on top. Then these free drying lysimeters, you just have a tray or a bucket somewhere and you wait until the water drops in and you sample that. Or you install resins, exchange resins that capture the nutrients when they're percolating through this column. So there are different ways of doing that to get at these soil solution. Soil extracts work differently, and one of the possibilities is to use resins. These exchange resins are available for cations and anions. They have not been made, of course, for soil scientists, but for instance, water purification, deionizers to get deionized water. But since they're there, they work very well, and you can expose them to soil, either putting them into the soil directly, strips or beads put together into a small like tea bag type of contraptions, and then put them in the soil and retrieve them and then extract as if it was soil. And you see they're typically very, very, this portion that can be extracted by resin is very dynamic. Here you see an annual dynamic of phosphate extracted with resin in the soil in the field, and you see the differences here are enormous. I mean, from almost 0 to 1.75. So there are orders of magnitude between the values. Very, very sensitive indicator of nutrient availability. Here an example where resin phosphorus over time is plotted after different organic matters were applied and in comparison to inorganic control. Here, for instance, Tithonia, which is a high phosphorus containing legume mulch material, and maize stover, and you see there's a huge spike very initially here of phosphorus but also after some weeks, there's still a huge difference between the different treatments. So it's a very, very sensitive indicator of nutrient availability. And then all the salt extractants, a lot of them we use in the lab also. We use potassium chloride for nitrate and ammonium in lab 1. We're using phosphorus extractions in various labs. We're using ammonium acetate for potassium, calcium, and magnesium extraction, and so on. There are different ways of doing that, and the process is then ion exchange. So one ion just pushes off the other ion. In that context, we have also already talked about cation exchange capacity, and we have learned about the effective cation exchange capacity in comparison to potential cation exchange capacity. The effective is the extraction of bases with mostly with ammonium, but there are also other methods with barium, we use this ammonium acetate in lab, and the extraction of the acidity and protons and aluminum with KCl. And together they added up are the effective cation exchange capacity, whereas the potential cation exchange capacity are all the ammonium adsorbed to soil at the pH of 7. And I want to show that to you in a small trick film here. So if that is our soil, over here we have our negatively charged clay surface, and these are all the cations that are in the soil solution that are adsorbed to this negative surface. So there's only plus, 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 and then there are some anions also in the soil solution that are neutralized by the cation. So there are 1 minus, 1 minus, 2 plus here. They're swimming in the soil solution. Oh, swimming around. Then you try to get rid of the cations that are in aqueous solution, and only the cations that are adsorbed remain in the solution. That's actually a step that we skip. And then we add ammonium chloride in this sketch here. We do that with ammonium acetate, and the ammonium kicks off all the cations. And then in the leachate, what we capture underneath, we measure all the cations. Then we have all the exchange sites are now occupied by ammonium. But if we would now make an extraction and quantify the ammonium, we would overestimate the potential cation exchange capacity, because there's still ammonium out here that is not adsorbed. If we would now quantify all the ammonium in here and say all the ammonium would represent potential cation exchange capacity, we would overestimate the cation exchange capacity, because these are not adsorbed out here. It's only those that are adsorbed. So we will need to leach again with ethanol and get all the ammonium out that is not absorbed to an exchange site, and then change again the ammonium with potassium chloride or calcium chloride, calcium chloride, whatever comes in handy. And then we will quantify the ammonium that has been leached out, and that is equivalent to the cation exchange capacity at a certain pH. So this is exactly what Joseph is doing in group 5, and that is what you all will be rotating through, and he will be demonstrating in detail. In addition to these salt extractants, we have acid extractants. Phosphorus, the Bray, Mehlich, and Morgan solutions that we also learn about in lab. Calcium and micronutrients also very often extracted by Mehlich and Morgan solutions. Then there are organic extractants. for those nutrients, well, yeah, let me ask that, do that question. Why would we be interested in organic extractions? What type of access to a pool of soil nutrients should that simulate?
Mobilized, maybe?
Yeah, they're more strongly held than, for instance, just soil solution or adsorbed. And if you think about the plants, what mechanisms do they have available to them? We just talked about that with the micronutrients. What can happen in the rhizosphere? How do they access copper, for instance, or iron, plants in the soil very often?
With acids.
Yeah, so the low molecular acids, oxalic acid, citric acid, they exude those, and in the rhizosphere make micronutrients available by complexation. So they exude these chelating agent, and then copper, manganese, iron are available, are made available and soluble in the soil solution, and then the plant can take them up. And exactly that is what these extractions are simulating. So they're accessing a pool that is not just exchangeable with the salt, but this simulates what the plant itself can also do. Well, the question about critical levels, that's really something we have also been discussing a lot in the lab. What are critical levels? How can we even assess what we extract there? We get a number from all these extractions, something like how many milligrams of potassium per unit gram or volume of soil. And what do we do with it? And we realize that what the plant can actually access and what this extraction is actually telling us is really, we need to assess through field experiments or pot experiments. Because every plant types, soil types, and extraction will be reacting differently, and the number that we get from these extractions is really a very arbitrary number. It makes only sense if put in relation to a specific crop or plant and a specific soil, and that's very important to realize. There are other nutrients where, in addition to just the exchange complex and the adsorption-desorption phenomena, there's another story to it. Why do we put them together here? Nitrogen, phosphorus, and sulfur. What's different for those three from the others? It's always the same question. They're mainly in organic form. So for those three, the most important, or one of the, for phosphorus that's only half or a portion of that the case, but especially for nitrogen and sulfur, since they're present in soil 95% or more in organic form, the process for nitrogen and sulfur availability is really not how much available nitrogen is there, but how much can be delivered by the organic matter to the inorganic portion. So that is really the key to, especially nitrogen and sulfur, but for phosphorus that also plays a role. So what we're interested in, especially for nitrogen, is the so-called mineralization. So not only the mineral part, the available part of total nitrogen, but how much can be made available, a process, and we call that mineralization. So for nitrogen, we can measure, for instance, the mineral N at the beginning and the end of an incubation period, and that's exactly what we do in our lab experiment. We measure it once, one pot, we take a sample, we measure mineral N, how much ammonium and nitrate is in there, and we put it back in the incubator, we come back, later, in our case 4 weeks later, and we measure the same pot, the same thing again. If the amounts of ammonium and nitrate increase, we have a mineralization. If they decrease, we have immobilization. So that can be made in containers and jars in the laboratory. It can be also, there are various other possibilities in mini lysimeters in the laboratory, where you have then undisturbed or disturbed soil pores, and you put always water on when you want to extract it, and extract it down, and measure the nitrogen and ammonium down here. So you can measure it actually at the same piece of soil multiple times, and you can do it in high resolution. You can do it every day if you want, or every 2 hours. That is a bit more difficult with our setup. You can do it in containers, bags, and jars, also incubated in the field. Very popular method. Just put it into the plastic bag, wrap it up, put it in the soil. Then at least it's exposed to the temperature that is experienced in the soil. Or also then mini lysimeters in the field, where you actually also expose it to the moisture that is prevalent in the field.
The cob that is used at tasseling when the tassels are 2.5 centimeters long. So there are certain times in the plant development and certain plant parts that are recommended, and for those there are catalogs for publications that you can look at. For trees, there might be other plant parts. So here you have just a few possibilities that I just mentioned. Beans, for instance, whole plant before flowering. Very often for trees, it's the youngest fully developed leaf. Then, going back to the visual plant criteria, and these are really very, very, they're highly plant specific, though there are some that can be grouped for different plant groups. And here are some indications. Nitrogen, for instance, very often the symptoms are coming up in old leaves. Potassium also in old leaves, whereas it's for micronutrients very often younger or youngest leaves. Critical levels very often also range. That's why some of the books only give sufficient amounts and not really thresholds for critical levels. So you have to always view those with caution. For deficiency, for toxicity, this is even more difficult, because in addition to the direct toxic effects of a nutrient, there might be also indirect effects, that one nutrient affects the availability of another, so that toxicity is not really expressed as a negative effect of that nutrient in particular, but the suppression of another. So what you're actually looking at is the deficiency of another nutrient. And we want to look at that a little bit more, and I already announced on the web that we will be having a happy quiz today. And for that happy quiz, we'll divide in 3 groups. Maybe Angela together with Debbie and Helen can go in one.
And what we do, I will show you a nutrient deficiency or toxicity symptom, and I will first ask group 1 what they think that is. And for the first round, we'll just do it. You have 30 seconds time to consult, and then you have to give me an answer. If your answer is right, you get a point. If your answer is wrong, the question goes to group 2. Then I ask group 2, you have 30 seconds time to consult, and then you have to provide an answer. And we do that as long as we get this one symptom right. And then I'll ask first group 2, and group 2 gets a first shot on the next symptom. The next round we do then a little bit more complicated. And of course we have grand prizes for the best group and the runners-up. And now, are you ready? Are you all set? So, what is this? Which deficiency is this? You have to first consult and then give me an answer. If your answer is wrong, the question goes to the next group. But you guys can already also discuss, because it might reach you.
Are all the nutrients fair game for this?
All nutrients are fair game. You might also pay attention to what I write here. This is obviously a deficiency because I write which deficiency is it. It's not a toxicity. 10 seconds left. Okay, what is the answer? Group 1. Nitrogen? Nitrogen, it is. It is nitrogen deficiency. Group 1 gets 1 point. Okay, group 2. Is group 2 ready? Group 2. Which deficiency is it? The other groups can already discuss as well. 15 seconds left. Five seconds left. Your answer?
Calcium.
Calcium deficiency it is. Thank you very much. Why is it calcium deficiency? Why did you think it was calcium deficiency?
Because calcium is not mobile, so it doesn't move the young shoots. Therefore, the young shoots are affected and they start breaking.
That's right. And why do they break? So they're, yeah?
Yeah.
Where is calcium in which structural components in which plant components is calcium present in the plant? Cell wall. So it's important for cell walls, calcium. So if you don't have cell walls or weak cell walls, you hang down. Yeah. So typical calcium deficiency symptom is that everything hangs down. By the way, I forgot to ask you, why did you think that there was nitrogen deficiency, the previous one?
Because of the yellowing of
Yeah, so yellowing, a bit stunted growth, yellowing practically the whole plant, but more maybe even the older plant parts. Yeah, that's right. Group 3, are you all set? It's not getting easier. Which deficiency is this? Fifteen seconds left. Five seconds left. Group 3, your answer. No, it's not zinc, but good try. Group 1 gets the question. What does group 1 think? Maybe we'll make it a bit darker. Yeah, now you know.
Phosphorus?
Huh? Phosphorus? No, it's not phosphorus. Group 2. It goes back to you, so you better have a better answer.
Potassium.
It is potassium. Potassium deficiency. Why is it potassium deficiency?
One is because it's starting from the lower order leaves.
That's correct, and it's starting from the older leaves. The symptoms are in the older leaves. Why, or older needles? Why older? Why did it tip you off that the older affected needles are an indication of potassium deficiency?
Because it's mobile, it translocates.
Yeah, so potassium is really the most mobile. So the youngest plant parts are very often not affected, but the older plant parts are. So the question now goes to group 1 again. Yeah, you get a point. That's right. Oh, 2. Sorry. That's right. 15 seconds for group 1. That's a bit of a more difficult one, but 5 seconds for group 1. And your answer is?
Magnesium. Go with that calcium.
Calcium?
Yeah.
No, it is not calcium. Oh, sorry. It would have been magnesium. Sorry. So it was magnesium. Yeah, you would have known that one, huh? Yeah, darn. Okay, group 2. Ready, steady, go.
Phosphorus.
Phosphorus, yeah, that is right. Phosphorus deficiency. Why is it phosphorus deficiency?
It's because of the red, purplish color.
Yeah. Dark red, purplish color. What else can you say? Stunted growth, so it's just not growing very well. It has purplish, dark reddish color. That is correct. Group 3. What is this? It is an element that we already had, but this time with a different plant. So this is obviously a tomato, and
Calcium.
it is calcium deficiency. Why do you think it's calcium deficiency?
I just know that rotting on the bottoms of tomato plants.
There we go. Yeah. So this rotting of fruit, especially with tomatoes, that's indicative of calcium deficiency. Excellent. So at the moment we have group 1 with 1 point, group 2 with 3 points, and group 3 with 1 point. So it remains exciting. So now what we do is not anybody gets a certain time, but the first who shouts it out is right. So you're under time pressure now. However, if you have shouted out one, you can't shout the next one until all the others have shouted out one. So if your answer is wrong, then you have to keep quiet until the other groups have voiced their opinion. Are you ready? Everybody ready? All groups ready? So you have to quickly touch base within your group and then give me one answer per group. And who has the first right answer gets the point. Ready, set, go.
Phosphorus.
No. We haven't had the element yet.
Is it boron?
Boron, no. So if group 1 has to answer, and if group 1 answer is wrong, then it's open to everyone again. Group 1?
We haven't had this one, or we have? We haven't had this one, or we have?
We haven't. So I'll give you another 10 seconds. Because So what does group 1 think?
Manganese.
Manganese is not right. It's open to everyone. Huh?
Sulfur.
No? No?
Zinc.
Yes. It's zinc deficiency. Wow, that was exciting. Why is it zinc deficiency?
It's deficiency.
Hmm? Why is it zinc deficiency? I mean, it was now trial and error a little bit. Saying. Why is it zinc deficiency? What could tip you off that this is zinc deficiency?
Well, the youngest leaves have, like, it has intervenoporosis.
Yeah, yeah, but a lot have them, and it's really difficult to see. What would be a typical, really typical symptom here? And it doesn't have anything to do with, yeah, exactly.
Yeah, that word, the space in between the leaves.
Yeah, exactly. Yeah, so this reduced space between the internodes, stunted growth that you have a lot of with trees. That is also very, very typical. That you have leaves coming out every centimeter practically. Reduced internodes. So that's very typical for zinc. Can also be observed sometimes with iron, but zinc is the real typical one. Okay, we'll do the same thing again. Are you all ready? Set, go.
Copper. Copper, potassium.
Copper what?
Copper. Toxicity.
No?
Copper deficiency.
No?
Manganese toxicity?
Yes.
Yes.
Manganese toxicity. Why is it manganese toxicity? Why is it manganese toxicity?
Black spot.
Black spots, what are these black spots?
Manganese buildup.
Yeah, manganese oxide. So they're manganese oxide buildups, and this is what creates these black spots here. And yeah, very good. Oops, I haven't really pressed it. So this is a toxicity. It's manganese toxicity. Okay, we'll do another round. Ready, set, go. What is this? It's obviously a pear up there.
The thing on the bottom is
And this is a potato. Yes, you're right. That doesn't earn you the point yet. But this is the healthy one, and this is the not so healthy one. And what else can I say? It's obviously it has something to do with fruit quality, and that could already circle it in what kind of nutrient it is. Fruit quality is very often impacted by a group of nutrients. Which nutrient is then the next question? It's not easy. Another tip is we haven't had it yet. I'm not sure if anybody already mentioned it. Yeah, you're all free to shout out. Wow, you're obviously hesitating.
Iron.
Iron? No, it's not iron. A micronutrient is a good guess. The other groups?
Molybdenum.
Molybdenum? No, it's not molybdenum. Group 1?
Boron.
It is boron, actually. It is boron deficiency. Why is it boron deficiency? I mean, I don't know if I can ask that question. Huh?
Boron has a lot to do with like reproductive structures, like flowering and
Yeah.
not vegetable.
Yeah. So boron has a lot to do with reproductive organs and fruit quality. Fruit tree quality is very often impacted by micronutrients and especially boron, but also manganese and copper can play a role there. So let's try this again one more time. What disorder is that? Once you know what that looks like, it's very easy to remember. It's very typical for gramineous species.
Sure.
Looks completely different in dicots. We've had the element already.
We've had the element.
Yeah, we have had the element already. But we have had almost everything already, so it's not a huge revelation.
Potassium.
Potassium? No? Yeah. Quickly, the other two groups. Another 10 seconds.